She'll talk about simplicial neural networks. Please take over.
Yeah, thank you, Herbert, for the introduction. And thank you for the invitation and for everyone to be here so early in Europe to listen to this talk. Today I'm going to talk about simplicial neural networks. This is a joint work with Michael De Ferrat, a PhD at EPFL, and Gard Spreeman, a former postdoc at EPFL. And the goal of this talk will be defining a type of neural network on data lying on simplicial complexes. And more generally, we will see neural networks lying on topological spaces. So the outline of my talk will be the following. I will start by defining what a convolution is and how this operation is a way that one can use to exploit the space structure. Then I will define the simplicial neural networks as neural networks for data in higher dimension. And in the second part of my talk, I will present other topological neural networks. These are other neural networks for data on topological spaces, which are not part of our work, but which I consider very interesting. And finally, I will outline some direction of our future work. And please don't hesitate to interrupt me for any question during this talk. So to start, I will start with something that probably everyone here has already heard about or is familiar with, convolutional neural networks. So convolutional neural networks are probably one of the most famous kind of neural networks for image classification. They can be used for many other things, but the task they've become popular for was classifying an input given by images. So for example, here, the input is this image, a robot, and the output will be a class, if it's a robot or a doll. And one can think about convolutional neural networks as a composition of functions, which are mainly given by these ingredients. A convolution, which is a linear operation on the pixel of the image. A nonlinearity, which is applied to the convolution. And other two operations, coarsening and pooling, which can be roughly thought about it as coarsening is the operation that reduces the size of the image. Imagine you have an image given by 4 pixels. One can have a coarsening of this image from 4 to 2 pixels. And pooling is the operation that is applied, that assigns a value of a pixel on the coarsened image. Imagine here on the original image, you have some value on the pixel. Pooling will assign to the reduced image a value based on the original image. For instance, one can take two popular options are max pooling or mean pooling. Namely, one takes the maximum over the some pixel of the original image, or the mean over some pixel of the original image. Well, in this talk, I won't focus on coarsening and pooling, but I will mainly talk about convolution and how this operation is a way that is an operation that exploits the structure of the space. And in particular, I will start by explaining how this convolution exploits the structure of an image, and then we will see how it does it for graphs and simplicial complexes. So let's start with the basic case and how convolution works for images. So one can think about an image as a grid or a graph given by a grid in which each pixel in this image here can be thought as a node in a graph, and 2 pixels are connected if they are neighbor in the original image. So in this way, one obtains a grid structure in which pixels are nodes, and there is a value in each node given by the value of the pixel. And the convolution is a linear operation on the value of the pixel, which is n-localizing. Namely, it involves pixels that are at most n hops apart. In particular, what does it mean? For instance, in this case, if we restrict the convolution to this pixel. Sorry, was there any question or? Okay. For instance, if we restrict the convolution to this pixel here, and we consider a convolution that considers pixels at most 2 ops apart, we will be considering these 2 pixels here because they are at distance 1, and this pixel here because it is at distance 2. And the convolution could be a linear operation, for instance, given by the sum of these 2 neighboring pixels. So this way of localizing the operation to just at most n pixels that are at most n ops apart, it's made one of the most computational advantage of convolutional neural network, namely this give linear computational complexity. So we have seen that in this case, with images, the data can be easily represented as a grid. But as you might know, not all real data comes with such a regular structure. So there are cases that are well known in which data comes in a form of a graph, which is not regular and in which usually nodes represent some user or some objects, and the edges represent the pairwise relation between these objects or user. One such example are social networks, in which one can represent them as graph, taking nodes to be user and edges to be some kind of relation between the users, such as friendship or common interest. Or we have as well biological networks, like brain structural or functional networks, in which nodes can represent neurons or part of the brain. And the connection between this neuron or part of the brain are kind of how strong the interaction is. Same way with communication network, in which nodes can represent cities or areas in the world, and edges might represent a way of communication between these 2 areas in the world. So all these are far away from being regular grids, but as images, we can have edges in which we represent pairwise relation, and on top of having a graph, we might have data on the edge, on the nodes of this graph. For instance, for each user, we can have the age or what some interest or so on. Or for the neuron, we can have as data on this neuron can be the voltage or some signal given by some measurements. Same for the cities. At the same time, I think recently, people started noticing that graphs are very limited and they are just able to represent pairwise interaction. So for example, in some cases, graph won't be able to capture all the interaction among the objects we are considering. So this is the case why we start looking at higher dimensional interaction between user or objects. For example, if you think about having a co-author network in which each node here represents an actor, and an edge between 2 actors represent the 2 actors play together in a movie. Well, if you just consider the graph in this case, you might lose some information. For example, you won't know if 4 actors play together in a movie or if they pairwise play together in different movies. But by using simplicial complexes, one will be able to model this kind of n-fold interaction. For example, n-simplex will model an interaction between n+1 people. In particular, in this case, we will have that 4 people can be modeled as a 3-simplex, or geometrically, one can think to model this as a tetrahedra. Same way, another example could be coauthorship network, in which each node here represents a scientist or a researcher. And we add n simplex every time n+1 people collaborated together in writing some paper. For example, if 3 people here collaborated together in writing some paper, we could add these 2 simplex here, a triangle. And so from a network, if we consider the simplicial complex associated, we can encode in this network the n-fold interaction. And on top of this, we could also add some data on the simplices. As for graph, we have data on the nodes. One might have some data or signal on the simplices. For example, in the coauthorship network, in which we had this triangle representing a paper written together by 3 people, one could have the 100 could be representing the number of citation that this paper had. Or in the case of the coauthor complex, one could have on the 3 simplex here, the rating of the movie in which these 4 people acted together. Well, in the same way, one can extend a social network to social complexes in which simplices represent common interest and feature, as well as biological complexes in which, from biological network, simplices can be added to represent neurons firing together or share chemical interaction and so on. Well, I think I might give you an example to think about why network can be limited to represent pairwise interaction and why it could be useful to consider their simplicial structure instead. But so imagine now you're considering a simplicial complex with some data on it, for example, the coauthorship network. And we have the possibility to have a neural network which exploits the topological structure of the simplicial complex and process data on the simplices. What will be the task that this kind of network could perform on simplicial complexes? So there could be many tasks. Among these, I will present here 4 examples that have been all already performed or tried out, but there might be many others that I won't present here. So one of these could be missing data predictions. Imagine you have a simplicial complex with some data on it, and one doesn't know some data on some of the simplices. A neural network on simplicial complexes might exploit the simplicial structure and might process the data on the simplices and could be trained on the task of predicting what are the values on these simplices. So another task could be performing isomorphism tests on graphs. This was done by Bodnar et al. In a paper in 2020 and another one in 2021, in which, in a nutshell, what they did was considering graphs, and then they lifted this, they considered the clique complex of this graph, and they trained some simplicial neural network to say whether or not these graphs are isomorphic or not. And I will give you more details about this later. And another task could be simplicial complex embedding. For example, think about if you have a simplicial complex that doesn't have any metric structure or is not embedded in a metric space, one could train a simplicial neural network to find the best embedding of this simplicial complex in a metric space. This task was performed by Ashish et al. In a paper in 2020. And another task that a simplicial neural network could perform would be classification of simplicial complexes. Imagine you have 2 simplicial complexes that represent 2 different social networks. One one coming from one subreddit and the other one coming from a second subreddit, and the task will be saying, oh, from which subreddit do they come from? And also this classification task was performed on many datasets using simplicial complexes and simplicial neural networks by Bodnar et al. In a paper in 2020 and another one this year. So I hope I have convinced you that having a neural network that processes data on a simplicial complex might be useful. Well, I would like now to start to defining this neural network. So the idea is we would like to generalize convolution neural network from data, from an image to data lying on a general simplicial complex. And the goal would be formulating a notion of convolution on simplicial complexes that exploits the locality of the pixel as the convolution on image was exploiting the locality on the pixel of the images. The tools we will be using to...
Quindi devo cercare le mie slide adesso su questo computer qua.
Che...
Cavoli, come fa?
Oh, Claudia, you're not muted.
Okay, yeah, I switched to Italian naturally.
I have muted them. Her.
Okay, thank you. Yeah, so I was saying that the goal will be generalizing this convolutional neural network to simplicial neural network, and the tools we will use to do so are the Hodge-Durham Laplacian, also known as combinatorial higher dimensional Laplacian or Laplacian for simplicial complexes. These were some kind of Laplacian that were defined by Ekman et al., like in the Ekman et al. And we will use also signal processing on simplicial complexes, which was initially introduced by Barbarossa and Schaub. And it's important to stress that all this work builds upon other work that has already been done on graphs. So graph convolution neural network has been around since 2016. These are neural networks that takes as input data lying on a graph and they exploit the graph structure. In particular, our work will be an extension from graph to simplicial complexes to this paper, Graph Convolution Neural Networks by Michael de Ferrat. And on top of this, since around 2015, the field of geometric deep learning, which is a field that looks at data lying on general geometric spaces, for machine learning and deep learning has been exploding. And I suggest this book by Bronstein et al. As a review on all the things that's been done in this field. Okay, so this was a general pipeline of what I would like to talk about in the following 20 minutes. And I will start by defining the theory we need to have for defining the simplicial neural networks. So I will start with the Laplacian for simplicial complex. In this talk, I will consider X a finite-oriented simplicial complex. And I want to stress that in this talk, I'm looking at simplicial complexes, and all our work was written for simplicial complexes. But the theory behind works for a general cell complex. We decided to focus on simplicial complexes, both for application and for simplicity. And okay, so we consider X a finite-oriented simplicial complex, and we will denote by CK of X the K co-boundary operator, which, if everyone here is not familiar with, can be thought as the real value function on the K simplices. And then we consider delta K, the K co-boundary operator, which is an operator going from the real value function of the K simplices to the real value function of the K+1 simplices. I also won't go into details on how to define this operator, but one can think about it as how to attach function in a lower dimension to a higher dimension. And the K-Laplacian can be defined as follows. The K-Laplacian is an operator, LK, that goes from the function on the K simplices to the function on the K simplices, and is formally defined as a composition of the coboundary operator with the adjoint of the coboundary and the K-1 adjoint of the coboundary with the K-1 coboundary. So probably this formula like here doesn't tell anything to anyone. However, I don't want to go into details of the math of this, but I will give you an intuition of how this operator works on values on the simplices. So we will first start with the case for k equals 0. We'll consider the 0 Laplacian. So this is an operator that goes from the 0 simplices to the 0 simplices, namely from the nodes to the nodes. And in case k equals 0, so the 0 Laplacian coincides with the well-known graph Laplacian. And how it operates on one node is it takes the value of the function on this node and it propagates this value on the neighboring nodes. So from here, it propagates the value from this node to itself and to the neighboring nodes. It can be thought as an operator that smooths out the value on the nodes on the neighboring nodes. So now we go in higher dimension. So the 1 Laplacian is an operator from the 1 simplices to the 1 simplices. So it operates on the edges of a simplicial complex. And it can be thought in this way. Imagine you have some value on this 1 simplex. Then the value will be propagated to the simplex itself and then to the neighboring simplices from here to here. In a similar way, the 2 Laplacian is an operator from the 2 simplices to the 2 simplices, namely from the triangles to the triangles. And it can be thought as propagating some values on a simplex to the neighboring simplices. So I want to start using this terminology because we will see it later as well. So for this way, the Laplacian operates in passing some signal to the neighboring simplices like here and here. We can think about the Laplacian as a message passing function on the simplices. This terminology comes from graph neural networks in which they define message passing function on the nodes. So a Laplacian can be just thought as a message passing function on the simplices. Okay, so we have now defined what the Laplacian is. And for defining a convolution on the simplicial complex, we need to first define what is a Fourier transform and what is a convolution. So we first define what is a Fourier transform for real value pico chains. So a pico chains again, we denote C is a pico chain. Again, it's a pico chain. C. And you can think about C as a real value function of the P simplices. On P simplices. The Fourier transform is given by the projection of the pico chain or the real value function of the P simplices on the eigenvectors of the Laplacian. So here, E1, E2, E denotes the I are the eigenvectors of the P Laplacian. And then the convolution between two real value picochains C and C prime can be thought as one computes the Fourier transform of each of the two, and then it's Fourier transform back. Okay, now that we have the notion of Fourier transform for picochains, we can finally define what is a simplicial convolutional layer. So a simplicial convolutional layer is given by this formula that I'm going to explain now. So what is a composition of psi? This is just a nonlinearity. Together with a convolution of C. What is C? C is our input function on the simplices. And what is fp minus 1 of phi omega? This is a low degree polynomial in the eigenvalues of the P Laplacian. I don't want to go much in details of this because I don't have much time, but let me just rephrase this formula in other terms. So the convolution here inside is nothing but the following. The convolution consists in a low degree polynomial in the P Laplacian. So the convolution here, so this convolution here is nothing but a low degree polynomial. This is the P Laplacian, to which we apply our input signal, and what are Wi here are the weights to be learned. So imagine this as we take an input signal C, we apply the Laplacian that can be thought as a message passing function on the simplices of the same dimension. And then we learn some weight in front of this message passing that tell us how to passing at best the signal on the simplices. So with this kind of convolution, one of the advantage as for convolutional neural network is that as linear computational cost, these are just convolutional sparse matrix vector multiplication. We have a constant number of weights to be learned. And as for the convolutional for images in which we were looking only at neighboring pixel, here in convolution for simplicial complexes are also n-localizing. So we are just looking at pixels that are, at simplices that are at most n ops apart because of the structure of the Laplacian. So maybe just again, to have the entire picture in mind, what is the architecture of a simplicial neural network and how it works? Before I show you the theory now, I'd want to compress everything in one image. So if we have a simplicial complex, and for example, now we want to consider some data on the edges of the simplicial complex. So we have some data. So the input of the simplicial neural network will be the data on the edges. And then the convolutional layer will be composed of the one Laplacian, in this case, will be applied to the input signal. And what we are learning are the weights in front of this Laplacian, this polynomial in the Laplacian. And the output will be again the learned signal on the one simplices. Okay, so I showed you now what the basic foundation of a simplicial neural network and how the architecture works. So I will present you now what was the task we trained our neural network on. So Michael Gard and I decided that the task we wanted to train the neural network on was predicting citation on the coauthorship complex. So what was the data we have? The data was, we took it from the Semantic Scholar dataset, which is a huge dataset containing papers together with citation, together with other metadata. And from the Semantic Scholar dataset, we built different coauthorship complex in this way. So, for example, imagine Claudia, Herbert, and Francesco wrote a paper together. Then we added a triangle here between these three people. And what was the data on the Simplicial complex? So, for example, if the book Herbert, Francesco, and Claudia wrote together 50 citation, then we would have as data on this triangle 50, the number of citation of this paper. But as well, for example, if Claudia and Francesco wrote another paper together, and this paper had 100 number of citation, then the value of the collaboration between Claudia and Francesco will be 150. So it will be 100 plus 50, given by the number of citation of the book they wrote together and the paper they wrote together. And so on, we build a simplicial complex in which maximal simplices represent papers written together, and interaction represent collaboration between researchers, and the data on top is the value of the collaboration or the number of citation in the collaboration. And what we trained our simplicial neural network was in the task of predicting missing citations. So suppose we have our coauthorship complex, but on some simplices, we delete the value of the number of citations. We don't know the number of citation between Claudia, Francesco, and Herbert, and we don't know the number of citation on another collaboration. So we delete randomly at different rates between 10 and 50% citation on the simplices. And the neural network had the task to predict this missing citation. So we had the following results. So we trained the neural network in predicting missing simplices, and we assess the accuracy of the network in how accurate we're able to recover the missing prediction. So the percentage is given how well how many correct prediction in percentage was the network able to recover. For example, if we consider only in dimension 1, so only the edges, if we were deleting so if we didn't know the 30% of the missing citation, so if we didn't know the 30% of the citation, then we were able to recover more or less correctly the 72% of the missing citation. And we trained a neural network in dimension 0, 1, and 2. We trained up to dimension 2 because of computational cost. Already going in dimension 3 was having high computational cost. Well, we also compared our method with some baseline and with some baselines. We only compare with some statistical baseline, like computing the mean among neighboring neighboring simplices, or using some other statistic. I won't go into the details of what is shown in this table, but what I want to stress is that we compared our neural network with some basic statistics, which are definitely nothing complex or sophisticated. And as a future work, we would like to compare our result with something more sophisticated as a neural network or graph neural network, or something that goes beyond just pure statistics. Okay, so I will check how much time I have. Yeah, I think still in the remaining 5 minutes, this is the second part of my talk, in which I would like to talk about not my work, but other work that have been done on neural network on data on general topological spaces. So there are different works that came out at the same time in 2020. one by Ashish, cell complex neural network, which defined a very similar notion of convolution as us, but using message passing and using upper and lower addition simplices. And then we had another work by Bang et al. On simplicial to complex convolution neural network, which was very similar to ours, but up to dimension 2. And in 2021, there were 3 papers in which were defined neural networks on topological spaces. We had principal simplicial neural networks for trajectory prediction by Glaze and al., in which they analyzed theoretical properties of the simplicial neural network. And finally, we had these 2 papers, Westphal-Lehmann-Go topological message passing simplicial network and Westphal-Lehmann-Go cellular CW networks by Bodnar et al., in which they define a general message passing through the boundary co-boundary operator and also through adjacent simplices and or cells. And what is interesting are the application of these neural networks to perform isomorphism tests on graph. And I would like to spend maybe a few minutes in describing what they are doing. So in both paper by Christian Bodnar, what they define is a message passing on simplicial complexes. So message passing, as I said before, can be thought as an updating of the signal or on the data on the simplices using some rules on neighboring simplices. So what is the difference between our message passing using the Laplacian and their message passing using all the simplices? So I give you here one example. The one Laplacian, if we have some kind of signal or data on this edge here, will perform message passing or will propagate this signal here just to this edge here. This is a way for how the Laplacian is defined. We look just at the edges that are in this. It will have a particular way to message pass in the signal. However, in the paper by Christian Bodnar et al., they use a different message passing that considers the following. So this one simplex here, this edge here, will receive signal by all the simplices I will listing here. So it will receive the signal from upper adjacent simplices. So upper adjacent simplices are the triangles that include this edge here. So in this case, this triangle here. It will receive the signal from the nodes that are included in the edge, so from these 2 nodes, and it will receive the signal from the edges which are adjacent to this edge. So from this edge, from this edge, and this edge. So the message passing function includes much more information compared to ours, or it might include much more information. And as well as our neural network, the neural network, what does it learn? It learns weights for how to pass at best the signal. And I want to just focus on 2 applications they had in the paper. Let me just go back 1 second. So they define this for simplicial complexes, but also for cell complexes. So there was simplicial complexes, but also for general cell complexes. Okay, so, and 2 nice applications of this paper are the following. So the simplicial passing neural network were proven to be more powerful than graph isomorphism test. So let me just go back a bit. So the paper is called Westphal-Lehmann-Go topological message passing on simplicial complexes. But what is Westphal-Lehmann? Westphal-Lehmann is, for who doesn't know, or probably a lot of people know here, but I'll quickly tell you, it's a test on graphs to say whether or not 2 graphs are not isomorphic. This is a classic isomorphism test on graph. And what they proved in the paper is that, for example, this graph, so the two graphs in the top and two graphs in the bottom, the Westphaler-Lehmann test cannot tell if this graph and this graph are isomorphic or not, and same for these two. They were able to prove that if we consider a graph and we take what they call the lifting to a cell complex, so when we have cycles, they fill them in. So the simplicial passing neural network or the cell passing neural networks were able to distinguish this graph and saying that they are not isomorphic. So they were saying that simplicial passing neural network and cell complex neural network are more powerful in distinguish not isomorphic graph. They are also more powerful than other neural networks. And another application that they did in the same paper was trajectory prediction. Imagine you have this simplicial complex here, and the task is to classify two kinds of trajectory. So the trajectory that goes below this hole and the trajectory that goes above this hole. And then the simplicial passing neural networks were very good in predicting if a trajectory on the one simplices was going down this hole or was going up. Okay, so I think I'm coming to an end of my talk. I defined a notion of convolution for data lying on a simplicial complex, and I showed you also how this can be thought as a message passing on simplices, and how other people has extended this to a message passing using more information. What we are thinking for our future work is how to define a proper notion of coarsening and pooling for the simplices. This will involve, for example, as an image, the coarsening is reducing the size of the image, and then the pooling part is finding a signal that is meaningful on the reduced image. So we're trying to define a notion, a meaningful notion on how to compress a simplicial complex to a smaller one, and how to send the signal from this over the data we have on the simplices of the simplicial complex to the simplices of the smaller simplicial complex in a way that can be meaningful, put in a simplicial neural network. And finally, I think this will be really the final task. Will be finding really a data set which has data naturally lying on the simplices, because all the example I give you, in somehow we use the simplicial structure to propagate the data we have on the simplices on lower dimensional simplices. And it's not so easy to find naturally data that has data on all the simplices on all dimensions. So this is the paper in which we have the simplicial neural networks with Michael and Gard, and the code, if you want to play with simplicial neural network, it's available on GitHub. Yeah, thank you very much for listening, and looking forward to answer any question.
Thank you, Stefania, for the very clear talk. Do we have questions? If you have one, send a Q in the chat in my direction, and I'll call you. In the meantime, I have one question. If you go back to the graph where you compare 0-dimensional, 2-dimensional, 1-dimensional, and 2-dimensional, you had these graphs with the accuracy earlier.
Yes. Yep.
When you look at the 0-dimensional, at 40% of the data missing, it seems the variance goes to 0. Is that an accident or?
So in here.
Yeah.
So very close to 0 in the sense that, so the accuracy is 60%, it's around 60.
And this interval, that's the variance.
That's the variance, yes. It's very close to 0, the variance. So the variance was taken over. Yeah, since the data was randomly, so we masked at random the 50% of the citation, we took 10 different instantiation on how we randomly deleted the instantiation. And yeah, curiously here, the variance is very low.
Okay, thank you. I think Jürgen had a question.
Yeah.
In fact, I have two questions. Thanks for the interesting talk. The first question would concern representing this co-authorship data. Wouldn't they naturally lie on a hypergraph instead of a simplicial complex? Because if you have a collaboration of 3 authors, there may or may not be papers between pairs of authors, and there may or may not be single author papers. So that is, if you have a simplex, then not all its boundary faces might be naturally contained in the data set. The second question is about this Weisfeiler-Lehmann test that you compared with the Bodnar method. Is the Bodnar method always better than the Weisfeiler-Lehmann test, or just in some cases? And if you supplemented the Weisfeiler-Lehmann test just by the length of cycles, would that give you a performance that is equivalent to that of the Bodnar test?
Okay, so to the first question, you're totally right. The coauthorship network, as most of as other kind of coauthorship network, they have an intrinsic hypergraph structure. So the Simplicial structure, what it had is a pairwise. It had interaction between any subset of authors that, in some sense, if I collaborate in writing a paper with other 2 people, I also collaborate pairwise with the other 2 people, but this is adding some interaction that is not intrinsically there. I think some kind of rate data set that doesn't contain just an hypergraph structure, as might be the coauthorship network, might be like contagious network, in which a simplex represents an interaction between people that might propagate some or spread some disease. If I have an interaction with other 3 people, I have also a pairwise interaction that might be different with the people in this group. So yeah, the example we had could be also thought as an hypergraph. And for the second question about the Weisfeiler-Lehmann test, so in the paper, they proved that in every case, the simplicial passive neural network are more powerful than a standard Weisfeiler-Lehmann test. Then there are also Weisfeiler and Lehmann tests in which they are called K Weisfeiler and Lehmann test, in which they add also interaction between nodes that are K ops apart. So these are more powerful. So K Weisfeiler and Lehmann tests are more powerful than Weisfeiler and Lehmann test. But in the paper, they don't compare K Weisfeiler and Lehmann test with the simplicial passive neural network and the cell complex neural network. So I don't know an answer to that. I suppose
Okay.
up to probably
yeah.
K, if one consider K cycles, they might have the same, they might be the same, but I'm not sure.
I mean, it sounds likely, yeah.
Yeah, we're moving a little bit late, but maybe one more question. Kelin, you had a question?
Yeah, I just have a following questions, with Jorgen's test. So the co-authorship network seems to better represent the hypergraph, and there are already some hypergraph-based graph neural network models. So what is the correlation, or have you do some comparison between the hypergraph neural network and your, simplicial complex neural network?
Yeah, I think we should compare, like in the here, when I say that we didn't compare our method yet with any more sophisticated method, I think hypergraph network will be included in the more sophisticated method we should compare our simplicial neural network with. But what I intrinsically say is that hypergraph network and simplicial neural network might work on very different data. So there are data sets that could have a more simplicial structure, and we have data for each subset in a group of interaction that might perform better than a hypergraph network. But yes, in this case, I think the first thing to do would be compare this, the model we had on a coauthorship network by using a hypergraph neural network. It would be interesting seeing the difference.
Thank you. Yeah.
Kelly Max has a question. Is it a short question? Otherwise, I would like to delay it to later.
Yeah, it's
Kelly?
really short. It's really
Okay.
short. Yeah.
Good.
I was just great talk, Stefania. That was awesome. I was just wondering if you have any ideas of like, so usually like the simplicial complexes, I'm interested in stuff, more geometric things like check complex or RIPS complexes. Do you have any idea if there's like intrinsic or like interesting functions that you might be able to put on that for these, or like more kind of like applications to simplicial complexes that represent geometric data?
Yeah, we thought about that, and we were thinking when we were thinking about geometric data, like function on the simplices coming from the geometry, like the distance of the region from the barycenter, or if you have something that is more you have some geometry plus some physics going on, imaging a 3D mesh, and you have some 3D mesh like I don't know, something representing a rabbit, and on each triangle you have the reflection of the sun on the triangle, something like this, like more geometric function.
Cool, thank you.
Last question, Mattia, could it be short?
Yeah, sure. I was just wondering if you ever thought about regularization. You know, I would be more interested in knowing how to regularize these networks rather than doing pooling, for example.
No, I never thought about it, actually. I was more thinking about the pooling part as a more topological part, but I never thought about regularization, actually.
Okay, thank you.
It will be a good question.
All right. Thank you very much.